to the steam generator, that's where that liquid water is going to turn into a gas. Once that liquid turns into a gas, it can start to move these gas molecules because they move a lot faster than liquid molecules do. It's going to start to move something as you move across. So you're in the steam generator, move through the steam line, and you see something called a turbine. All of these really high-powered steam vapor are going to move this turbine. This turbine then starts to make a generator work, which then produces electricity to power our homes. So steam is making the blades of this turbine move faster and faster. So it's creating this turbine to move. This turbine is then powering the generator. Once that turbine starts powering the generator can start producing a current, which is just a flow of electrons or electricity. And that's how we get our power source. That's how we can get our electricity, is through this steam moving the turbine, powering the generator creating a current. That's what we get in our home. So that's what we get for our electricity. Now, at some point, it's like one really big cycle. So I have to do something with the rest of that steam, because I can't just keep piling more and more steam into this turbine. It has to go somewhere. So ultimately, as more steam continues to move the turbine, other steam is going to go down into a condenser. You know what condensation means. Condensation means that we're moving from a gas phase to a liquid phase. So it's really like we're cooling down that high-powered, high-temperature water. Once the steam gets into the condenser, the steam will be cooled down by other cool water that's in that condenser. That cool water could be coming from some type of tower where it has some type of cooling source, or it could be from a lake or a pond, which actually most nuclear reactors are next to. Once this water starts cooling down and becomes cool enough, it will move out of the condenser and it will move its way or work its way back to the reactor vessel, where the whole entire process starts over again. So it's really like we can cycle the same amount of water over and over again to kind of save or replenish that resource. So in a really simple form, let's go through it again really quickly. There are fuel rods in a reactor vessel that have a very heavy unstable isotope in them, typically uranium. Those unstable isotopes will go through nuclear fission reactions. Once they go through these fission reactions, they create lots of energy. That energy is absorbed by the water that's moving around those fuel rods. That high energy water now moves through the structure into a steam generator. And remember, as it moves through that structure, it stays a liquid throughout the whole thing up until it gets to that steam generator, because we don't want that water to start boiling, so we keep it at a very high pressure to contain the temperature or maintain the temperature. Once it gets in the steam generator, that liquid water then turns to a gas or a vapor. Once it turns into a vapor, that vapor can move into a place where there's a turbine. The vapor is strong enough, has a high amount of energy, that it's going to start moving the blades of the turbine. Once the blades of the turbine start moving, that will start powering the generator. Once the generator is powered, it can start creating a current. And that current is just electricity, which is then what will run our homes or businesses, so on and so forth. Now that steam has to go somewhere, so the remaining steam will move into a condenser where it will cool down and change from a vapor or a gas to a liquid. Once it cools down enough and turns into that liquid, it will move its way back to the reactor vessel, where the whole thing will start all over again. Okay? So that is really simply how a nuclear power plant works. Now, nuclear power plants have some really, or nuclear reactors have some really big disadvantages as well as some really good advantages. a great advantage to nuclear power plants is that we can get like 1,000,000 times greater just the amount of energy than we can from just one little single tiny chemical reaction. There's so much energy that's created in these nuclear reactions that we can have enough electricity to power an entire city like the size of Seattle. So nuclear power plants have a really large advantage. There are some really big disadvantages to nuclear reactors, though, as well. One really big one is that radioactive waste is created, and we don't necessarily know what to do right now with that radioactive waste. One thing that scientists have been doing is that they will package away this radioactive waste that they have or that's created, and then they will either bury it really far underground or they will put it inside of a mountain. How effective that is, we don't really know because there hasn't been a lot of time that's gone by since we've started these nuclear power plants. What's happening to that radioactive waste? Also a little bit unsure of. So radioactive waste disposal is a really large problem for these nuclear power plants right now. Another problem is that this radioactive waste could possibly be used for nuclear weapons later on. And the creation of nuclear weapons is something that is incredibly scary to American citizens or to anybody. So that's another problem in terms of nuclear power plants. Second problem is that when a nuclear power plant goes through a meltdown or has an accident, it can affect a lot of people. There are two really big nuclear reactor meltdowns that were really large in history. One of them was Chernobyl, the other one was 3 Mile Island. In Chernobyl, that happened in Russia in 1986. Ultimately, what happened was that there was a problem with a reactor. Because of this, there was a very large amount of radiation that was exposed to a huge area. So think in terms of geography where Russia is. The radiation that was emitted from this power plant melting down was found or felt in Italy and as well as Germany. So this amount of radiation moved a very large distance. And that's a problem because more and more people can be exposed to a certain amount of radiation, even if it's, countries away. The other nuclear reactor accident that happened in the United States was 3 Mile Island, and that actually happened in Pennsylvania. In Pennsylvania, what happened was that the water ended up becoming so hot that we couldn't cool it down. When they couldn't cool it down, the operators at the time thought that they should just shut off the cooling agent. Guys, that's Cody. Coolest barista ever. The operators then shut off the coolant pumps because they thought that maybe that was creating too much work for the nuclear reactor to have to do, and they thought maybe the water could cool down on its own. That made the problem even worse. The reactor then completely melted down, and then there was, of course, radiation that was exposed or released. This accident, the 3 Mile Island, 3 Mile Island is what created this mass hysteria of nuclear power plants and nuclear energy being a bad source of energy. So, and you have to think why. In Chernobyl, that accident happened in Russia, and we didn't feel really any of the effects from that. So, of course, in our minds, it doesn't happen to us, so we don't really think about it. 3 Mile Island did happen to us. It happened in Pennsylvania, and a lot of people were affected by it. So, because a lot of people were affected and it happened in our country, it became this, nuclear power is a bad source of energy, and it's too dangerous, and we don't get enough advantages from it. There's just too many disadvantages. So while nuclear energy has all of these really bad things that can happen, there are disadvantages. There are also some really good things that happen, and I think that we need to make sure that we weigh out all of our options so then that way we can understand both sides. Okay, so talked about nuclear fission, talked about nuclear power plants or nuclear reactors. Last thing I want to talk about, guys, is nuclear fusion. And nuclear fusion is when you have two really small isotopes, two very, very small elements, like hydrogen and helium are typically used for nuclear fusion reactions. Two really small nuclei will come together and they will fuse together. So fusion, fuse, it's like they're melding together. Once they fuse together, it creates an even larger nucleus. So in fission, we had one really big thing, and then it splits up into two little pieces. In fusion, we have two small pieces that meld together to make something bigger, okay? Now, fusion, nuclear fusion, is how stars work. So I will post something on the blog as well to kind of talk a little bit more about stars. I think that one article that talked about the atomic emission spectrum talks a little bit about those stars, and I don't know if it mentions nuclear fusion or not, but I think maybe it does, just a little bit, but I'll find something else too. A lot of people wonder or have questions about why we can't use nuclear fusion reactors instead of nuclear fission reactors. And fusion would be a super superior method to generating a certain type of power or electricity. And the really good news is for that whatever waste or whatever products are generated wouldn't be radioactive. So that's a huge advantage. The problem is, in order to do this, we're going to have something that will withstand or hold elements or nuclei that are at the plasma state of matter and that are several million kelvins in temperature. In terms of being that hot, think about several million kelvins. That is huge. So we have to find something that will first contain and withstand that high temperature. The second thing is that nuclear fusion reactions don't necessarily happen the same way that fission reactions do, because fission reactions can have these chain reactions where it can just keep going over and over and over again. Fusion reactions aren't as continuous, so we may get a fusion reaction to happen, but we're going to have to sustain those fusion reactions to keep happening, to keep generating our electricity and our power, or otherwise we're going to be 1 minute sitting in light, the next minute we're going to be sitting in the dark. There are scientists, there are groups of people that are working on this right now, and what's really interesting is that around 2000s they thought that it would be done by 2010. They have become very successful and they're very close, but they think that they need more time. So the research scientists that are working on this believe that we will have nuclear fusion reactions by 2050, which is really cool. So that actually could be happening in your lifetime. All right, guys, so we talked about fission, we talked about fusion, we talked about nuclear reactors. Now, remember on Monday, we are going to have our nuclear power debate. On Monday, the first 5 minutes when we get into class, I want to finish the last two types of decay that we didn't get to yesterday in class. So we're going to do that for the first 5 minutes. Then on the next time of class or the rest of class, I'll give you about 5, maybe 7 minutes to talk in your group about getting what you want to get together so you can kind of get your thoughts all organized before we debate. And then the rest of class will be spending that time arguing back and forth about nuclear energy, whether we're for or against it. Remember, I will choose a winner. If you both bring excellent arguments to the debate, then I will award both of you winners, but that means you have to both be quite outstanding. If not, I will pick a winner. And if I think both groups don't do well, no one is the winner and no one gets extra credit. But you guys are so good, so I know that you'll both bring your A game. I will also be posting on the blog that you need to bring out a printed article for your debate, and you need to have 2 questions. So don't forget that as well for Monday. I will see you guys on Monday. I hope you have a really good weekend. Bye, guys.